So what you see right here is a clutch that allows this planter unit to turn on or off, or to operate at different speeds. And that's generally a classification or a category of technology called swath control, which allows you to control within a large area smaller pieces. And it's used on spraying equipment, planting equipment, fertilizer application equipment. So if you've got a 100-foot boom on your applicator, you can control very small sections of those to either turn on or off or to apply different rates. The whole thing does not have to be doing the same rate any longer. And research has shown that savings in these kinds of technology really start to add up as you get to more and more ununiform fields. So just to illustrate that, this would be an example of where you're planting or spraying if you did not have swath control. You're either double planting or double spraying this area of the field where you have to drive into in order to fully plant to the end of that row. Well, with swath control, as you approach that row that's already been planted, each row or each section will shut off as soon as it reaches an area that's already been planted. And it's not sensing that that's been planted, it's just remembering. It has that map of where it has planted or fertilized. It knows that's done. I don't need to do it again, and once it reaches that position, it shuts off.
How accurate is that? How many feet?
We're not talking about feet, John. We're talking about inches. Within, I'd say planters where I've seen those shut on and off, they're within 6 inches. And so you start to add up the savings in seed and fertilizer and pesticides, and research I've seen from Kentucky, I don't know if I have that. Yeah, I've got that data here. They're seeing savings of $25 to $30 an acre in input costs just by not double applying or spraying that area of the field. Now granted, these shaped fields may be a little different than what we have in Nebraska. So on a square field, your savings are going to be much less than these. Well, another part of that RTK GPS technology then becomes, okay, I can steer the tractor, so maybe we should steer other things as well. So there's technology now that allows you to steer the planter and also to steer the implement. And that becomes increasingly important if you have a lot of slope or if you have a very large implement. And a couple of ways. One is passive control, where it just changes the steering of the tractor. So it's getting to be a bit, you have to think through that, but you want to be on this track, but you don't really want the tractor to be on that track. You want the implement to be on the track, so you make the tractor steer where you don't want to be so that the implement is where you want to be. So your tractor is off of the track, but the implement is on the track. So that is passive steering. Active control actually has coulters or driving devices on the implement that can steer it, as well as the tractor being steered as well. Increasingly, farmers are using this kind of equipment. This scale and size of equipment used to be restricted to dealers, but as farms get larger and the scale of what they're doing larger, it's not uncommon for farmers to have equipment like this. So this is a high clearance sprayer with a 100-foot boom. In this particular study or case, he's applying nitrogen fertilizer, and it's a little hard to see, but we've got 3 sensors that are looking at crop reflectance and changing the rate of fertilizer on the go as he drives through the field. Not using swath control though, and probably for a 100-foot boom, that is something that we'd want to have. So in this case, on this particular study, this was 4 years ago now, we were applying a 100-foot wide swath at the same rate. A year ago, we installed this new linear move irrigation system at our research farm at Clay Center at the South Central Ag Lab. It's not very evident in this photograph. At the other end is a GPS antenna. So this is using RTK GPS to steer the linear move irrigation system. So we don't have to have any buried wires or cables to direct where this GPS-driven irrigation system goes. And then the next thing that's going to be added on to that is the capacity for variable rate irrigation. Now this particular system is installed at a research farm that is very uniform, or the field that it's on is very uniform. But we're wanting to research what happens if we change rate or have different rates of water applied. So this allows us to more or less instantaneously change the rate of water application based on nozzle by nozzle control of the water flow through each one of these nozzles. Now the concept is then on a farmer's field, as you get to an area that holds more or less water or has greater or less yield potential, you can put on more or less water. The question that we have, and that's why we're doing the research, is how do we really tell farmers how to manage that? We don't have good directions on how they should do that yet. So we have a research project, this being one of the sites, the other sites on farmers' fields that are equipped with these variable rate irrigation systems to get a better handle on that question. Yeah?
Is that per section or per drop down?
It can be either. You can choose just to, the crudest would be by span. So you could just measure this whole span and control it separately. The more you want to invest, the finer your control can be. So in our case, we're going to install a valve on each nozzle. A farmer may not feel that that's necessary. He may choose to say, well, one valve might control maybe 4 nozzles or something like that. But kind of depends how much he wants to spend. Now this is being sold commercially. So Valley is one company that has this technology on the market. And they're suggesting a number of layers here can go into that map then that drives the variable rate irrigation system. And I would agree with that, that there needs to be more than one layer of information that's used to control the application of water. The real challenge is, what is the equation that ties all of these layers together? So that's kind of the heart of our research. The other side of that is, okay, if we apply X amount of water here and Y amount of water there, how does that influence our fertility needs? If we're putting less water on, does that mean we need to put less fertilizer on as well? It starts to get kind of complicated. And so that's why we have a number of students and a number of scientists involved in that thing.
What's the unit of measure for that?
Well, when we measure this way, we're measuring it in millisiemens per centimeter or meter. Usually numbers 20 to 150, something like that. So much higher numbers than the conductivity that you'll measure in the lab or with something that you would have that's a pocket-sized conductivity meter.
Rich, as a producer, how much does one of those valves cost as far as the control valve?
Oh, on each nozzle? I believe it's about 30 bucks. So per nozzle, that's not much, but I'm not sure how many nozzles there are. It starts to add up. Actually, this system, we're just now installing those on, and I think we're going to invest about $6,000. This is not a large size system. I think it's a 6-span linear move system. This is another tool that's available. It's again, probably something that a contractor would use rather than a farmer. This is an instrument to optically measure soil organic matter. So it's a little hard to see, but down in this coulter is a shoe that's running at a depth of about 4 inches in the soil. It's emitting a light source in 2 wave bands. One is visible, one is near infrared. And it's looking at the reflectance then back in those 2 wavelengths, and it's relating that to soil organic matter. And so we create a map of organic matter. This happens to be where this linear is installed here at Clay Center. This is the map of conductivity, organic matter for that field. And in this case, we're seeing a range of 2.8 to 3.2% organic matter. And that's a pretty boring map. And that's what we want for this site and for this study. Not much variability, because we're going to impose variability with our research treatments. On a farmer's field with a lot of landscape variability, you'd see much wider ranges and a more interesting map then. This kind of research then is ongoing. This is a platform that we're using in a research phase. What I showed you before is commercially available. This particular instrument was one that was developed by our precision ag engineer and working with a couple of grad students. It's measuring on the go mechanical resistance, so how much draft there is, soil moisture, and soil reflectance in both visible and near infrared bands. So this cart has a couple of different sensor platforms that are mounted on it. None of these are commercially available yet, but we're looking at should they be developed commercially. This is a tool that's on the market commercially. It's for research to map soil color in a very detailed way. It's looking at reflectance in 384 wavelengths as we go down through the soil, as we insert a probe into the ground. These are 4 of those 384 wavelengths, looking at reflectance in depths down to a depth of 1 meter. Again, how does that relate to organic matter, soil moisture, other properties that might be of interest to the grower? Soil water is something that we're looking at measuring in higher density, both time and spatially. So there are sensors that are on the market now that farmers can put out into the field to measure soil moisture continually. That information is collected and sent to a satellite receiver. The farmer can access that from a website. And then in our research, we're looking at how those sensors might be tied together in networks to be able to measure the variability in soil water content throughout the field and relay that information back to the irrigation system for control of water application. Last thing to touch on is remote sensing. We've used several platforms that are using unmanned aerial vehicles for measuring the crop status through the growing season. Again, these are probably not something that farmers are going to be using right away, but someday the crop consultant of the future is going to have something like this that they can look at a crop from the air very easily and quickly to get information on the variability of the field and things that they maybe should scout in more detail. These are a couple of platforms that we're hoping to start using this year, both that are equipped with cameras that can measure both visible and near infrared reflectance of the crop as it's growing. One thing that I do find intriguing to students is the chance to play with toys. And so as you're thinking about introducing high school students to agriculture or soil science, the field of remote sensing and robotics is something that I see really growing in the future. There's a lot of interest in using small-scale robotics for mapping properties of either the crop or the soil. These are a couple of robotic platforms that are research platforms right now to either measure or actually perhaps manage the crop throughout the growing season. And the tendency is for smaller, autonomous, lightweight platforms. So a 300 horsepower autonomous tractor is not as likely as something that's 5 or 10 pounds, and we'll send a fleet of them out in the field instead. This particular platform, well, both of these are from the University of Illinois. And there's scientist Tony Griff there that's focused on robotics in agriculture. Our precision ag engineer position is currently vacant and being recruited for now here at Nebraska, and I'm hopeful that this is an area that once that position is filled, we'll be looking at in more detail. There's a lot of potential to equip these with all kinds of sensors that tell you things about the field, and they'll work 24 hours a day.